So you've screened a variety of different substrates or catalysts, and you finally come up with a promising transformation, and your zero pass has given you the green light and said you can proceed now to first pass. First pass should be used while you're during the optimization stage of your reaction design, and this is a lot more stringent than zero pass. It's worth noting that zero pass is not, as I mentioned before, it is not your final metrics. It merely means that you've avoided as many of the nasties as possible before going in, before moving on to optimization. And the idea with first pass, again, is to try and get feedback from the metrics with respect to your optimization and see if you can improve on it. It's going to highlight further hotspots in your methodology and areas where you might need to, that might require further development to improve its greenness. Again, it's a lot more stringent, so it looks at things in a lot more detail. Things you might get away with at zero pass will definitely be flagged at first pass. So you've probably covered yield, atom economy, and reaction mass efficiency at zero pass, and you definitely need to consider the same conditions that I mentioned for zero pass, but these mass-based metrics alone aren't enough, and at first pass we also include mass intensity and process mass intensity, which will take into account solvent usage, the workup stage as well, so it can really give you a good idea of where you're using most of your material. So if your process mass intensity is poor, but your reaction mass intensity and atom economy are good, you need to look for the cause. Chances are your reaction stage is fine, but there's something in the workup, or maybe your solvent use, that's causing an issue. The metric toolkit has been designed so that it can actually break down your process mass intensity data to the solvents used, the reaction stage, and the solvents used and the reagents used in the workup stage. So you can really use this to home in on where your material sinks are within your process. So the metric toolkit also analyzes reagent use. So these are the materials that you've input into the reaction to facilitate it, but don't actually form part of the final product. And I just wanted to stop for a bit and talk a little bit about catalysis, or use of enzymes or chemocatalysis. And a lot of people will say that if they're using if they're developing a catalytic process, then by default it's green, because as is with one of the principles of green chemistry is that catalysis is always better. However, we are getting to the stage where we need to start delving deeper into the catalyst that we're using. How green is a catalyst itself? We need to consider aspects such as turnover number. So how many moles of your substrate can you use with 1 mole of your catalyst to convert it to the product before the catalyst becomes deactivated? Space-time yield, and this is quite important when you're considering scaling up. So how much of the material can you produce per mole of catalyst, and how quickly can you do that? And ideally you want to produce as much of the product as possible with as little of your catalyst as possible in as little time as possible. Other aspects that we look at is recoverability and reuse, and this is to do with whether you're using a supported catalyst or not. Because a supported catalyst can be recovered and reused, although when you're developing a novel methodology that's not always straightforward to move straight on to catalyst support. But if you bear that in mind when you're developing a methodology, then this can help you on your way to developing a catalytic methodology where your catalyst can be reused and recovered. And then another aspect is use of critical elements. Now, a lot of the catalytic systems we depend on nowadays do use platinum group metals based catalysts. Isn't the only factor you have to consider when considering So in the metric toolkit, you will be given a red flag if you're not using a catalyst and using your reagents in stoichiometric quantities, but you'll be given a green flag if you are using a catalyst. But other things you want to consider is its recoverability and whether you are using a critical element, and finding alternatives if you are. Things to consider recoverability are shown in the blue box, so to consider either supporting it using a biphasic solvent system or membranes. Solvents is also addressed in first pass, but it becomes a lot more stringent. The solvents are now separated into 3 categories: preferred, problematic, and hazardous, which would each be given a green, amber, or red flag, respectively. Because solvents do form the bulk of the material used in a process, it's very important at this stage to try and use a preferred solvent. So you can, if you are using either problematic or hazardous solvent, try using solvent maps to find a number of different candidates for a solvent screen. Not only will you hopefully find a solvent alternative, but can indicate the kind of physical properties you need to facilitate your reaction. The metric toolkit also considers energy. Now, it's very difficult to measure the energy input into your reaction at lab scale, but the metric toolkit provides a few guidelines on how you can limit the energy intensity of your process. So a green flag will be denoted if your reaction is running between 0 and 70 degrees Celsius. A yellow flag will come up if you're using your reaction between -20 and 140 degrees Celsius. And then any reaction temperatures outside of these ranges will give a red flag. Now, if your methodology is running outside these ranges, try to investigate developing your process to within the reaction range, the green reaction range, or as close as possible. Another thing that came out of our discussions in the CHEM21 consortium is the fact that if you're running a reaction at reflux, you are resulting in a 6-fold increase in the energy requirements of your process. So try and investigate using your reaction at 5 degrees below the reflux temperature of your solvent. Make sure that you're not making any compromises with respect to other metrics. Or alternatively, try using a solvent that has a higher boiling point so that you can run your reaction at that temperature without reaching the solvent's reflux. We also address batch and flow in the metrics toolkit, and this is done so that we can encourage people to use continuous flow processes. So if you're using a batch process, an amber flag will be produced. If you're using a flow process, a green flag is given. Now, we realize it's not always possible to run a process in flow, especially if your group doesn't specialize in it. But if you've been making the right corrections to your methodology with respect to all the other metrics, such as using a supported catalyst, limiting the use of stoichiometric reagents, etc., then you are well on your way to developing a methodology that should be compatible with continuous flow processes. As Louise mentioned in her presentation on the metrics toolkit, we do need to consider the downstream processes of your reaction. It's not enough to think of your methodology as the chemical transformation and isolation. If you really want to make a real impact and develop a green methodology, you do need to consider the workup and isolation steps. Mass-based metrics such as mass intensity can capture the material usage that encompasses the workup and isolation. So you do need to take a critical look at what methodologies you're using and solvents you're using at this stage. Various workup and isolation steps were examined for the metrics toolkit, and you will get a green flag, or the recommended workup methods and isolation methods would be quenching, filtration, centrifugation, crystallization, and low temperature distillation, evaporation or sublimation. And by low temperature we mean less than 140 degrees at atmospheric pressure. So when you're developing your methodology, you should be really looking at using these isolation and workup methods first. An amber flag is given if you're using a solvent exchange or quenching into aqueous media. And methods that you should really try to avoid are chromatography, high temperature distillations, evaporations, and sublimations. And when we say high temperature, we mean above 140 degrees of atmospheric pressure. Multiple recrystallizations and ion exchange will also give you a red flag. Health and safety, as with solvents, has a more stringent assessment at first pass. The H codes that will either give a red or amber flag are shown on this slide, and ideally you want to look at replacing reagents that fall within either of these categories where possible. Something to note is that sometimes you're going to be using a chemical entity that you've made in the lab. It's fairly novel and doesn't have an MSDS datasheet. This doesn't mean your reagent is safe, and your metrics will not automatically be green as a result. Generally, the metrics toolkit will produce an amber flag for chemical entities that don't have an associated MSDS datasheet.